depths of 500 meters. The summit depth of this is 11 meters. I couldn't believe that. But actually, I found the text that goes with this, and it's 11 meters deep, and it wasn't known, which blows my mind. So this is an example. I'm sure most of the seamounts that will be surveyed will be nowhere near this big, but it's a remarkable example. Okay, so in conclusion, we're tuning up the base map, the SRTM15 for the next JETCO release. We have a number of improvements that we want to include, and we're working on these uncharted seamounts, and those, John, they're trying to release all the data for the SLI.DO 2030 assembly, so this would be great, and this may happen over a number of years. And finally, I asked the question, what's the most important thing we should be doing in the base map to help with the overall project? So, thank you.
Thank you, David. I didn't see anything in SLI.DO, and for those of you who are online joining us again, we've had some issues with the phone dropping off. It's not literally, but it's frozen a couple times, so we'll have to splice the videos together. We're on our third live stream of session 5 so far. Any questions for David? We'll just take a quick couple. John? And speak loudly just so the microphone can hear.
Not necessarily a question, well, maybe it's a question to the RDACs themselves. So like, we do recognize that the RDACs have access to data that's not available to Dave Sandwell. And so maybe a conversation could be had with the SLI.DO 2030 project, who oversees that, is how Dave Sandwell's project can get access to that data. All real bathymetry improves his predictive model. So that's one thing we really want to try to focus on. So that's just something we can think about more broadly.
Thank you, David. I'll just summarize for the video's sake. So John Hall was suggesting that RDAC data that's available through RDACs that perhaps see the 2030 project to make sure that that's available to groups like data set scripts. I'm going to, in the interest of time, I'm going to carry on. Matthew Brennan from IDA is presenting remotely. I believe it's a video. And he's online for questions, so I'll be monitoring SLI.DO or Steve, and we'll take her there. All right, roll Matthew's presentation.
Hello. Data collection is the building block to true autonomy, is what we're going to talk about today. But before that, and as is tradition, we're going to talk about floppy disks. So here we are. I made this. It's full of floppy disks, got some holes in it, there's fire apps, and it's totally pointless. It has no purpose whatsoever. So like these things have absolutely no purpose whatsoever, other than the engineering that's gone into them. Unless, of course, you add sensors. As we know, the sensors collect lots of different types of data. What does data look like? Data looks like this generally, if it's an ASCII unit. If not, it'll be binary, like something on the right. Now, data is entirely pointless unless we extract information from it. How do we do that? Well, first we must acquire the data and join it together into a single file. This is our on top. As you can see, we've got position vessels, background ETNs, some information on the bottom left there, alphanumerics, background maps on the bottom right. This is our offline software, download. Here we've got 3D models, digital terrain models, videos, profiles on the right here. So it's a very nice one to collect lots of geospatial information there. So before we can visualize data, before we can interpret using data, we first have to collect the data. So this is the hood that we collect the right data. So we'll begin with digitizing a survey boundary. We will specify our vehicle start position. And using the high dimensional planner software, we can create a theoretical route for you. Now this is the hope that the vehicle will follow this route. This route is based upon overlap, multi-beam sector, turn radius, whether you turn inside or outside, boundary that is specified. So there's a few parameters developers, some people design it in AutoCAD, other software. You can use them to design theoretical routes as well. Now, the problem with Hope, and I could go many different ways with this, so there's strength and there's weakness. The data shows that the vehicle is following the route that we planned for, but there still remains a huge problem.
Can you switch that?
What happens if it goes off the route, for example, on the edges? What was it? Let me show you. What if we think we're on the route, but in fact this happens? And there's vehicle motion. This is kind of giving me flashbacks to my offshore tiger days, so let's skip over that.
Thank you.
So in the we assume that the vehicle is at a payload sensor, the volume sensor is facing right now, so and we assume it doesn't grow from side to side, all pitch, all change here. So green is the area that we calculated or designed to collect information on the secret phone. But when we start to roll, what we see is that that sector, maybe it's 90 degrees, 120 degrees, whatever it is, it will move as the vehicle moves. So the red is the missing gaps that form. Now, as roll increases, unfortunately, I will fade, until we realize quite quickly that we don't have the secret coverage we paid to do, thus we might not get paid. And gaps will develop. Now, there is a solution to this. We start by digitizing a certain boundary. We specify a vehicle start position. Feel like we have been here before, but here we are. We create one starting runway. Well, this happens. So here the vehicle is collecting monkey there, and it gets to the end and it turns around. But what you might not be able to see is on the edge here. It's calculating the edge, and then we specified an offset, and it will actually create an offset line. So this isn't a parallel line, it's an offset line. People think we made an error here because there's a gap, but we're interested in the information inside this boundary, so all this data is going to get trimmed down. So these lines are not parallel, they are created based on where the data is. Here's another example. So over here we're in a harbour, see on the far right here. This is collecting data in real time. So I'm then calculating an offset line. It's a little bit slow, so we made one here that's a bit faster than it's sped up 10 times the vehicle speed. So as you can see, it's digitizing the edge. It's got a slight funny angle based on the orientation of what we're looking at, but it's going and collecting the data in the right place. So you'll see in a second when you change the TV with there isn't gaps here, it's just the orientation. And when we change to TV move, we've collected all that information in the most effective manner. This is really good because it saves on time. Time, of course, is important because it's quite the cost, and also it reduces energy use, so it's good in the environment. Now, whether it's left here, whether the route is live as using IVA's coverage system, or whether it's a design route, either of these will be fed into the eyeball of the panel. Autopilot is quite simple in a way, in that it only does speed and direction. A lot of the autopilots out there on the market will have to do everything, so we'll have to collect all the sensor data, what's going on the side scale, integrate picture roll heading, timing, and then send that information to where the vehicle needs to go. Because we're going to have impact from how we scan. Like I said, we've done this over 40 years, so we're very good at finding data. And then we send that information to the autopilot. All the autopilots turn into speed and then direction. So there's not much actually wrong. Now there's other types of product tracking, in this example it's imagery. So I want software intelligence, pipes on blue, nano's on green. This is our machine learning department. We will train our algorithms to find pipelines and various other things. What do we do with that information? Well, we boil it down to a single dot, if you want, so the center of the pipe. And that information can be fed back into the old part to make sure that you're applying data over the correct area, otherwise you'll have gaps in the data. And what happens when the pipe is buried? Well, can't do anything until it becomes exposed, and then we can start tracking again. So each sensor is only good for certain things. And so this is why we can have sensor fusion, this is why we can join sensors together to cover their weaknesses. So for example, you can't see it in the imagery, maybe it's buried, or maybe you're surveying the wrong area. So we should swap to a different system, for example, multi. So here on the left, we have survey data coming in that is raw, hasn't been cleaned. On the right, we're cleaning it in real time. Now, the reason we clean it in real time is so that we could fit objects to it. So in this case, we're fitting a pipeline through the micro runs. So we can feed that back to an autopilot, so we're serving in the right place, unless we're not. We can also track markers. So in this example, we are detecting where the marker is, in this case, a Ruger marker. So we can position things. So the camera is sensing where the marker is, and we can get relevant the X, Y, Z to that marker. We could also use it to position objects relative to each other. So in this example, we've got the two objects markers on, and we can see the separation between them. Another example would be if we are trying to dock a vehicle into a structure. So here we are getting closer and closer, and the idea is to sit on top of that box on the left. So get closer, 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 and position ourselves or dock ourselves into some sort of structure. So we have all these solutions to aid in the position of the navigation. Now, that's all very well good, but we still need to QC our data. So, over the last few years, we've seen more and more of our clients using our software to check the quality of our client server data. So maybe you didn't use either software to acquire the data, but you've got the data from somewhere else. You can certainly use our software to QC that data. So in 2017, we started a project BP UK, developed a QC toolbox. We asked BP what their needs were for QC different types of geospatial data. BP were very honest and they recognized that their own QC varied from region to region and also between departments for different things, which is to be expected. So since then, we built these products, and the toolbox is now utilized worldwide by BP to QC geospatial data. What types of data in the US? Well, they, should I say, quality control, multi-laser data, seismic data, pipeline data, and event data. Mainly they use it to check the calculations of subcontractors, whether it be trolley results, tide valves, or rig placements, and anchor surveys, or site surveys. So any type of data in marathon environment, they'll take it independently check. Here's an example of such data. So we have a DTM, we combine it with pipelines and events, so we can see the boulders on, we can see where the field joints, and various other properties. Here we're combining point clouds from a LiDO system with a DTM surface, which the sonar model as the main component. We can also combine imagery, so this is a high resolution digital stills, which we can display as a waterfall, and also the DTM. Here we've got meshes. Meshes are going more into our world. So meshes and DTM, so mesh with imagery and so. And this example I really like because on the left here we have, in both examples, sorry, we have the geometries from the multi. So the digital terrain model is formed from the multi. On the left it's colorized by depth, and on the right it's colorized by intensity. So when I first saw the data on the left, I thought it was maybe fish, but maybe I should clean it out. I changed to a different color and you can see quite clearly that actually some that should be clean. And again, another example of that, the geometry is tells you half the problem maybe, but you still need to combine with other coloration, whether it's RGB, camera systems with those intensive LIDO size scales. Now, since we're here talking about identifying gaps, I thought we would have a look at how we could help with them. So back in the day, this is how I QC'd data for gaps. I would scoop through it, take me a long time, and I would see with my eyes that there was a gap. So that would be quite good, and I would make a note of it, but we developed a tool where you can look at actual physical gaps in the DT themselves, or whether there is data densities. Thank God I found the gap firstly. Secondly, there's more gaps hiding behind hills, because the way I looked at that data was slightly different. So here we can jump through them, rank them, and we get properties about them, about the area, the width, the height, etc. So it's very nice to quickly look at boundary survey and see if there's a problem. So again, just to re-emphasize that point, we have gaps in the seabed, there's 3 here. Now, we're not really interested, we are interested in the gaps, but we are interested in bathymetry, but we are probably more interested in the gaps. So what we decided to do is we can make an inverse of the gaps. So here we've made a DTM out of the missing information. And this is really useful because we now have the eastern and northern and the depth for every single cell that is inside that digital twin. So we could feed that to an autopilot, for example, to hoover up the gaps at the end of an uncrewed surface vehicle in front of us underwater, and just to make sure that we're not leaving the field with gaps. For everyone out there that likes polygons or shape files, you can also get shape files as well, which are great again. Now, I did want to show some data, and I hoped SLI.DO collected the Gecko creator, but Tongan volcano, unfortunately, this data is not ready yet. So I added a few slides in here just to highlight that you are requiring multi-site scan online data. And are struggling to process this, please let me know. We have automatic data processing QC2. Ocean Infinity, as one example, of a similar problem when they first started their, mega mapping project. So we developed the workflow manager that automates a lot of the processing and QC tasks. So here's just a little snippet here on the left. We have files coming in, all files in this case. On the top, we detail the processing workflow, or QC workflows, so we're importing files, linking ties, and cell velocities, and creating DTMs, etc. And here it is giving us a status if it's okay. Because ultimately, we only want to look at data where there's a problem. If the data is good, I'm not too concerned by that. I want to look at things that are different or problematic. So here is crawling out a real job where it's important. Lots of different files and lots of different actions. If you do have problems with processing the data or get insight from it, please let me know. Which means we're on to data deliverables, just a quick few slides on this. Start looking at uncrewed surface vehicles with ASV Global, as they were back in the day, and Alfie Harris. This is some data we acquired at the National Oceanographic Centre, so just outside where you are today. So we have a line above and one below. Here's some hydrosurf down at the foot of Sound, I believe. So again, some very nice data from a very nice platform. Here we have X-Ocean collecting pipeline mock-view data, basic pipes using the software. Here we have some other subsea operating. I believe Moonus is Sam Sabertooth. Again, for pipeline data, we can scour wherever it goes. We have various vehicle corporations. So our software is embedded in some of the vehicles. I'm not sure you do all the way or just bits of it. Sometimes it's 9 scale, sometimes 9 miles, sometimes the whole plan. So we collected data from a lot of these vehicles. Time-wise, Goodman, Baltic Steel, Seaflow Echo Boat, Blue Tricks. Blue Robotics and Blue Rock 2, we actually have mission control software for both Blue Robotics, Blue Rock 2, and the mission specialist defender. Should you control these. Koenigsberg family, we have the workflow manager processing data, what we do. And of course, the self-saving youth and assignment partnership. And since you've been very, very good, I would just like to say thank you very much for your time and your attention. As you can see, I found a purpose for my paperweights, which had use. If you, on my presentation of use, and you have any questions, please let me know. You can contact me at mjb@lido.com or my mobile number. Thank you very much.
Thank you, Matthew, remotely. Really appreciated your presentation. That was great, and I think your contact information is there on the slide. If you've got questions, I didn't see any coming on SLI.DO, and we're running a little over time, so we're going to continue on with Paul Wintersteller from Teledyne on your presentation. Welcome, Paul.
Hey all, glad to be here. Thanks for giving us the opportunity to present a project, Horizon 2020 project in this. One of these services that has been created within the UW block for short gravimetry battery processing service. I'm on behalf of the people, standing also on behalf of the people mentioned here in this first slide, and I'd like to use the opportunity to thank Christian Casantos Pereira and Konstantinos Kanatsopoulos of the NTU, the National Technical University in Greece, and Christian at Marlin for the initiative to participate in the project. So what we are, NEAMIAS is a project we are in, is a NEAMIAS project Horizon 2020. NEAMIAS is an abbreviation stands for Young Man. It's an ancient Greek term, and the NEAMIAS project addresses the prototyping of new innovative services within the realm and the setup of the EOSC, which is the European Open Science Cloud. And within that challenge, NEAMIAS has been picked to be funded within the period of 2019 to 2022, it will end this year. So the NEAMIAS project aimed to provide 9 thematic services in the field of underwater, space, and atmosphere. And they are based on the state-of-the-art research assets of programs that are existing, but maybe based on what we do in NEAMIAS. We have done in NEAMIAS is actually bringing these services into the cloud. And in case of the UW block, the battery processing, we realized this with the MD system. It's a very well-known post-processing software, open source in the community of the high especially in research and academia. And this is how the service looks like if you access it through the web interface, the web portal. It is actually utilizing a Jupyter Lab surface to bring you close to MD system command lines that you can actually easily access through those prepared notebooks that we have released there. Documentation link is given out there. And you can simply log in with your Microsoft or Google social accounts and or your institutional university accounts if you have if they are authenticating through Microsoft. So what and how does that service work? What is the aim on it and why we did it? I will present it in the next slides. And first of all, what we have created is a Docker container where you actually put in every tool that you need to display and to run the service. And there's quite a few of them. And the cool thing on it is actually all based on open source software. And so the Dockerized tools again, suggested by the lab, rank to desktop, which I will come back in a few minutes explaining what that can do for you. Generic mapping tools, which every system is utilizing to create nice maps on. Forge for projection and transformations, digital libraries, NetCDF, Ambularitus as a SVP, Sammelogik profile database. All is Ubuntu based and it is mounted or it is connected with a shared forwarded to the typed database of OTS, so you can run typed corrections on the fly with this service. How does it look if you run those notebooks? We have prepared for you a notebook number 1 actually that actually runs automatically once you press the run all the codes, run the whole notebook. On top, it's all explained in the documentation for the service. It will actually run not even 2-3 minutes, and will show you raw bathymetry maps. It will do some processing for you. It will do type correction for you. It will run for a road calibration, and it all is done within 2-3 minutes. There is other notebooks to your convenience using to process own data sets. Notebook 2 is allowing to initiate that process for data processing of own data sets or other sample data that we provide. And the notebook number 3 will allow you to return to that another day, because as you all know, processing can be very time consuming. So you have the option to return or to manipulate manually through this other notebooks. You have them all, you can see them all in slide number 3. A notebook appears as a tab in your interface. You can see 3 tabs here having the 3 notebooks on the right side. Then you have a launcher and you have a terminal. You can access the terminal right away within the Jupyter Lab environment. There's another one, a notebook that helps you to publish the data that you have actually edited, or the notebook that you have manipulated to your own needs right away with a REST API that we have utilized from SLI.DO, or with a link that we provide to the German Tangier database that allows you to submit your data right away in the web interface. Let me briefly explain a bit the background of how that works and how that can be realized. So Neonias is a rather huge project, as I mentioned. It's 9 thematic services that we are providing. And we have 21 partners. And so there's, and in total, at least core people, it's more than 50 core people, and I believe they go up to 150 that partially work on those services. So what we need for a cloud service is actually a platform, and you can of course go to Amazon or to Google. In our case, the layers, the 2 basic layers, OpenStack and Kubernetes that you see here, are provided by GUARD infrastructure, which is the Italian national cloud infrastructure within the project. Imagine OpenStack as the cloud computing architecture, and while you have Kubernetes on top, working seamlessly with OpenStack. Kubernetes is actually a container orchestrator it helps you to spawn the single entities that you need. If you like to access one of these services, you will spawn one of these containers that you can see, these Docker containers, and then we go into a pod which is actually orchestrated by Kubernetes. There is quite a few things in behind that happen before you can access. Of course, it starts with AI, so it's an authentication, a single sign-on authentication, and there is core services that help us to manage those. So all these core services, there's been actually within the development of these 9 services, thematic services, there's been a development of 16 core services along with that within the last 3 years that help to manage and manipulate in the way we like to have to present these 9 thematic services on top. So, quite some manpower there. We have connection to so-called persistent volumes, which allow us to add storage, cloud storage, seamlessly to the computing power within the Kubernetes. And for testing purposes for you, there is a 1.5 terabytes available that you can use to test the service along with others. There is accounting, monitoring, and logging core services that act behind. So every of these cells, code cells that you release within a notebook can be logged, so we can trace back what happened, or if there is issues with the service that point back to a particular part of the code that does not release as expected. So why this service? Why MV in the cloud? As mentioned, of course, I don't know who may have worked with MV system ever in the yeah, there is quite some, yes. It is actually, yes, it's frightening at the beginning because it's command line, but I really appreciated working with that tool suite. It's more than 50 tools that you have in the MD system tool suite since 20 years, and I believe Dave Karras and David Chase are keeping that suite alive since more than 25 years. It can do a lot for you, but of course, indeed, it needs quite some time to get into. It needs a Unix or a Mac platform to install it and so on. So we want to get rid of those hurdles at the beginning for especially students or scientists or researchers interested in, also engineers. And we found that is actually a great option to overcome that issue, that service. If you start it, and if you're not too many people at the same time starting it, then it will take you less than a minute to start the service in the cloud. So no loads of installation required on a Unix or Linux-based desktop. And of course, we maintain, so it means we always have the latest version available. Yes, usage of the cloud computation in favor to local, that's for sure here, right? Resources. And the Jupyter Lab environment actually is a great learning platform to teach and to overcome this first hurdle to command line based software. Rainpool, by the way, is giving us the option to virtualize graphical user interfaces that are provided by every system, for instance, for manual editing. So take home message, yes, the service fulfills a complete hyperacoustic phone processing with more than 50 tools. And it's offline available. We also provided documentation about that, how to run the Docker locally on your desktop, and that will give you an opportunity to actually access the Docker container without having the interface. You can actually run it as an API if you want so. And of course, always then teach the command line. Let me briefly reach out to the two last slides, dealing with the other two underwater services, which one is the seafloor mosaicing. That is actually a contribution from Coronis Computing to our NEARS project. A great one as well. And the next is from Athens, NTUA, seabed classification for multispectral modeling data. Have a look at it. It's worth giving it a glance. So try it. And in case of, if you need something like decide the post-processing like data utilization and the AHO related proofs that have not been implemented in the system yet, TPS is available for educational licenses. Don't hesitate to ask for it. Thank you very much.
All right, thank you, Paul. In the interest of time, we're just going to carry on. Paul is here, so by all means, ask him some questions. And for those watching live, stream them into SLI.DO, and I will we'll make sure that they get to Paul. Next up is Tomer Ketter with a lightning talk, and on Mount the Gap, some of the activities that the group has been working on. And then we will shift to coffee break, coffee and tea, and biscuits over to the side. Tom?
Crumpets.
Hey everyone, good to be here today with all of you. I'm going to share a little story. I only have a few minutes. I don't want to keep your coffee getting cold. Everybody here has been talking a lot about data processing and acquisition and autonomous systems or unmanned. And I want to share a little story about human connection with the ocean, human experience, the human aspect of being involved in ocean mapping. I'm just going to present a little the partners that I had for this project. I'm going to talk about a survey in Fiji that I did, Trips and Adventures, generous support of a UK-based expedition out there, private super yachts, that kind of stuff. Submerged is a company based in Costa Rica that provides technology and expertise for underwater human exploration, manned submersibles, stuff like that. Pacific Blue Foundation is a nonprofit working with communities that live by the coral reefs, and they deal with sustainability and conservation. And of course, Map the Gaps, US-based nonprofit, the only international organization working towards democratizing ocean floor. So my story begins with a super yacht named Surrey and a submersible named Uni. They're both designed for, of course, the human exploration below the water, human exploration of the seafloor, to create a human connection with the seafloor, something that I feel we're all talking around, but perhaps this would to emphasize a little more what is all this mapping for. The trip was designed to go to Fiji, more specifically Vega Lagoon, which Shireen here? No? Okay, Shireen is from Fiji. She was really excited about it. But Vega Lagoon, we had some dives planned for that, so my task was to create a map and to pinpoint the best locations for diving. And the only piece of information I had was this nautical chart pretty much, which, as you can see, does not provide insight about the seafloor. So I geared up for a survey, and just before heading out, I was informed I'm going to have to ask for permission from the people who live where that one star is, in a community called Waisomo. So Waisomo is a tiny village that has maybe 250 people or so. And I had to, that's what it looks like, that's a beach. And I had to go there to ask permission from the chief of the tribe. And in order to do that, I had to wear the tribal skirt. I forget the term for it. Shereen seriously remind me. But anyway, I found myself walking through this village and into this building and sitting on the floor, woven mat, and explaining in English what this survey is about. Why are we doing this? And just to make sure that it's not going to be used for any mining or drilling or fishing or any kind of exploitation of these people's waters and their resources. So I was granted permission because I promised that we're going to share the data with them. And not only that, I was asked to come back when the survey is done and to present the results to the council of the tribe. So I put together a mapping team. I had an orbit and the protocol and the small boat. Oops. And that was the setup. I had a laptop on a small skiff, very open to the elements, and had some local support from the Fiji Navy. And we headed out. That's what it looked for some of the time. It's really nice and calm, but then towards the end of the week, it got really stormy. But ultimately, we were able to complete a pretty decent survey, and I created this 3D scene that I was really excited to go back to the village and share with them. So this is a picture of the presentation that I made to the tribe council, and I cannot really exaggerate how moved they were to see for the first time in their life a 3D rendering of the seafloor, of their own seafloor. And they've been living and fishing and diving there for generations after generations. So really hundreds and perhaps thousands of years of their knowledge was never translated into a visual object like that. They were so moved that they even said, "You are now part of us." And they invited me back to keep working there with them. And we're trying to get more funding to go back there and keep serving, not only with that community, but with the other. Every island is a different community, so there's hundreds of islands in Fiji alone. And that data actually is going to be used. They were so excited to get it because it's going to be used for their small part of conservation under a framework called 30 by 30, which is an initiative to protect 30% of the ocean floor by 2030. And this is just one small example of how data can and should be used to really protect not just natural resources, but also communities and traditional ways of living. This data set, of course, is available. If you want to scan it with your phones, you'll have this. It's on SLI.DO, what's it called, RTS Online. You can interact with it. All good, everybody good? And that's it. Those were my 5 minutes. And a little thank you from the little kids of West Home. And that's it. I hope we can, this QR code is actually more important because it will allow everyone to support the gaps a little bit with some contributions. That's it. Thanks for the time.
Thank you, Tomer. Tomer's here as well. If you've got any questions, and for those on video, you enter them in SLI.DO, then we'll make sure that goes to Tomer. let's take a break, have some coffee. I do want to, there's a few people asking about water bottles last night. If you go back to Eventbrite, search for Map the Gaps, there's now a new ticket called Bottle Ticket. It's free, the ticket, and then you can add on a water bottle. That's the easiest way to purchase one. Then just go through the checkout process, and you don't need to live in Colombia or the United States. So let's just do that. Coffee, tea, and we're going to regroup again at 11 o'clock.